Good afternoon, everyone. Welcome to another session of Network Seminar Series hosted by the Center for Network Intelligence at the Robert Bosch Center for Cyber Physical Systems at IIIT. Today's speaker is Professor Sanjit Krishnan Kaul, and he will be speaking on Edge Control Protocol, delivering fresh updates over the internet. Professor Kaul is Associate Professor in the ECE Department of IIIT Delhi. He received the BTech degree in Electronics and Communication Engineering from IIT Mesra in 2000 and a PhD degree in Electrical and Computer Engineering from Rutgers University in 2011. He worked in the telecommunications industry for 4 years after completing the bachelor's degree. He was a research assistant with the Wireless Information Networks Laboratory from 2005 to 2011. He works on problems in wireless systems research, and his current research interests include age of information, networking for cyber-physical systems, and autonomous vehicles. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for further details. I'll be pasting the links in the chat box. You can, during the talk, you are requested to keep the microphone in silent. And if you have any question, you can raise your hand in the Zoom interface and can unmute and ask. And if you prefer to put your questions in chat, then we'll be happy to moderate them. Over to you, Professor Kaul.
All right, thank you. Right, and okay, I guess we can get started. I think it would be nice if I could spotlight my own video so that I know what how I am being looked at. Is that okay? I can do that myself. I'll just do that. Else it's really weird because I can't see my video and I'm just talking to my phone. Okay. All right. Thank you again. Yeah. So okay, this is work with my student Tanya. Okay, and Roy Yates at WinLab Rutgers University. Right, and yeah, so it's Edge Control Protocol delivering fresh updates over the internet. So I'll just start off with a brief. I'll motivate it using some applications, and we have been doing this for many years now, right? And the one thing that has changed over these years is that earlier I used to say next generation applications desire timeliness, and more recently I have actually started saying they require timeliness. Just to say that my own trust in this hypothesis. It's still an hypothesis because I mean they require, but I mean, yeah, it still has to be verified for these so-called next generation applications. Do they really care to optimize timeliness per se, right? But in any case, it's clear that they do care to at least optimize a certain function of timeliness. So that much is clear, right? So these are your stereotypical applications, often use cases for 5G networks, for example. You have this V2X thing. I mean, broadly speaking, a vehicle would like to know the current or fresh state of others. Others could be other vehicles, other actors on the road, anything and everything really, right? Anything that can generate a certain status update. Right, and of course the challenge here is to maximize freshness of each other's state at the vehicles, right? And you have a constrained communications network, and that's why it's an interesting challenge. And this is a typical picture that's shown if you're in the V2X community, wherein you have many of these cars. There's probably some highway in New Jersey, right? And yeah, that's the picture. More recently than that picture from New Jersey, the other applications like real-time driver assistance using augmented reality. I mean, these ones again have this whole notion of the need to sense, okay, and sense at a reasonable rate, and then disseminate whatever was sensed, maybe after some processing, this on-road scene in a timely manner to a vehicle, right? And so the idea here is that there is this deer that not all these vehicles may be able to see. That's the thing in blue, but of course, whatever, the infrastructure camera network has spotted it, and of course, the hope is that such information gets communicated to vehicles in a timely manner. So in summary, these vehicles require information, right? I mean, informing the vehicle about the deer long after the deer has crossed the road is not very useful. Healthcare, again, real-time health monitoring. I mean, these are things that probably will be truer sooner than later, right? All these sensors, of course, you're connected to the cloud. There is some Wi-Fi access or wireless access network that's connecting you to the cloud. And I think broadly speaking, it's fair to say that real-time health monitoring requires fresh information at the monitor. The monitor here is essentially whatever that server is in the clouds. For example, if Google is interested in your health information, then that's some Google server, right? Or it could be, by the way, your friend. Maybe you go on a run and your friend, you give your friend your location, live location, right? And your friend is tracking your live location. So that then your friend would be the monitor, and you are the source. Okay. Internet of things, right? Broadly speaking, you have things with status updates, right? And most of these things have sensors on them and have some kind of a connection to a network, right? And they sense and send update, send information as an update, right? And there is some receiver, we'll call it the monitor. It could be a sink in a typical sensor network, right? And this sink or this monitor is for whatever reason cares to get timely information from these various things, right? And these things could be temperature sensors, for example, location sensors, temperature sensors, and so on and so forth, right? Of course, I'm not saying that it's only sense stuff. It could be, I mean, a robot may want timely information about the next actuation, right? Okay, so here's the gap that we spotted. I think it's been many years. I guess my student has a better count of the number of years. But when we started thinking about end-to-end control, end-to-end age control, that is, I have this source. The source is maybe my sports watch or my phone, and there's this server that's sitting somewhere in the cloud, let's say, or elsewhere. And you want somehow to make sure that updates from the source are timely, and we will quantify timeliness soon, are timely at this server in the cloud. And of course, this end-to-end problem has been worked on and has been solved for various applications or traffic kinds of interest, right? You have TCP, which is still like the control protocol that's used in the internet, right? Of course, you have UDP, you have RTP for more real-time applications, for example, and I'm sure there are many more, by the way, right? But essentially, they typically cater to what I will call traditional traffic, which is voice, video, file transfer, and so on and so forth. And the goal is typically to, these applications that they cater to are typically desire high throughput. And many of these desire high throughput maybe at a low enough delay, right? And of course, when it comes to voice, you want low delay, and you also don't want too large a jitter, right? So the question was this is the question we posed to ourselves. We're like, okay, great. Let's. I mean, our bet was then, and I guess this still holds true, is that over time these so-called real-time monitoring applications are going to be the significant ones, and we do need. It seems like we need a control protocol, and we called it the age control protocol. This is before we started doing anything on it, right? And just to reiterate, real-time monitoring these applications, and I say monitoring, but I mean it's real-time monitoring, actuation, and so on and so forth, right? And so the typical cyber physical system thing. Real-time monitoring values freshness of an update, right? And it's highly loss resilient. I mean, the point being that if you care for my location, I mean, you don't really, there is no sense in the network wasting, if you care for my live location, there's no sense in the network wasting resources trying to retransmit and transmit again some older location of mine in the hope of, achieving guaranteed delivery, right? It would rather just use resources to send my most current location, right? And maybe just drop the older packet. Okay, so the metric that we will look at, right, to quantify freshness. By the way, the freshness as a notion has been there forever, right? But this metric also has, you will find it in various forms, right? But I will tell you, why this sort of makes sense in the context of these applications, right? Okay, so age of information as a freshness metric. Here's a simple illustration, right? You have this blob, which is the network, and you have a source that's to your left, right? And it's generating location updates, let's say. And these location updates are desired by a certain monitor, right? And as I said, the monitor could be a server in the cloud and so on. So yeah, so the updates are being sent by the source. Maybe it sends the red update first in time, then sometime later it sends a green update, and then it sends a blue update, just different update packets essentially that have been generated at different points in time. And of course, these updates travel over the network. Not all of them may make it, and maybe let's say red and blue arrived at the monitor. Of course, all may make it, and it may not be in order delivery, right? So all that, everything that can happen when you send something to a network can happen, right? Right. So now let's associate some timestamps, and this is important, right? I mean, let's associate some timestamps to these update packets or packets of information that were generated, or packets of location that were generated, right? And let's say T0, T1, T2, no big deal. And the packet that was generated at T0 eventually arrived at the monitor, right, at T0 dash. And the delays could be the delays between the instant it was generated and its arrival at T0 dash. I mean, here we are saying it's a network, but it could be many other reasons. It could be processing, networking, whatever, right? So if I think about the monitor and the information it has at T0 dash, right? Okay, then at T0 dash, the monitor has a location update whose age is T0 dash minus T0, right? Okay. At T2 dash, this is simple. I mean, the T0 dash minus T0 is straightforward because the generation time was T0. That's when the location was truly fresh, was live, right? And the monitor received it at T0 dash, right? So may I please request the host to please mute others, because I mean, else I'm just listening to the other person. Okay, so just reiterate, we had a packet with generation timestamp T0, and it was received at T0 dash at the monitor. So at this instant T0 dash, the age of the packet, which is to say the packet that was received at T0 dash was old, and was old by an amount T0 dash minus T0, right? So the age of information, in this case, the location information, the instantaneous value of it at T0 dash is clearly T0 dash minus T0. Similarly, for T2 dash, it is T2 dash minus. Okay, this is not the complete picture, and it's important because when I show you only this part of the picture, T0 dash minus T0 is also the delay that this packet spent, this packet suffered when it went through the network. Similarly, T2 dash minus T2, right? However, what's important is that we look at age from the perspective of the monitor. So it's not the perspective of the network. It's not about the amount of delay something suffers in the network. It's about how old the information is at the monitor, which is to say that no packet was received at a certain instant T, the monitor has some information, and there is a certain age and age associated with the information. Now, if I pick some time T as a illustration, right? At this time T, at this chosen time T, the freshest update, okay, the freshest available update was received at T0 dash and was generated at T0, right? Therefore, the age at time T of location information at the monitor is T minus T0, right? So this age is clearly not just network delay. It is network delay for sure, but it also has to do with lack of new updates, right? Which has something to do with the source generating these updates. If you draw a sample function, this is an example sample function, right? The y-axis is the age of information, the instantaneous age at any time t at the monitor. Again, that's important, right? And let's say the source sends an update packet at T0, and this packet is received at T0 dash, right? And that's fine. When the packet is received at T0 dash, the age of this location information at the monitor is reset to T0 dash minus T0, because that's the age, that's the time the packet spent between generation and reception, right? However, beyond T0 dash, right, the age will increase linearly, right? This is the simplest case I'm assuming, and that's the metric we will look at, right? Age increases, it keeps increasing till the next update is received. And I'm assuming here that the update at T1 dash is newer, right? Otherwise, you just ignore it, and age doesn't get reset. Right. And again, the reset value here is simply T1 dash minus T1, because that's the time between generation and reception of the packet or the location update that was generated at T1 by the source. Remember, this picture is really simple when it comes to the real world because you're sort of assuming time synchronization. Right? I mean, it's like the receiver can actually calculate this curve, assuming that the receiver, in this case, the monitor and the source are time synchronized, but that's hardly ever the case. But we will see how we'll work around these problems in this age control protocol. Yeah, so I mean here, this illustration, I mean, age at the monitor increases due to rarely generated updates. Okay, I mean, clearly updates are coming once in a while, and in the intermittent, during the intermittent time, the age must increase. Okay, the other extreme is wherein you have this hyper, some kind of a hyper source, right? Maybe a student who is always eager to update, for example, right? And so you have this very rapid rate of update generation. You have T0, something gets generated soon after the packet gets generated at T1, and then T2. Of course, as soon as I generate T0, it gets queued in, it's sent over the network. T1 is sent over the network, but the issue with this is given that the network, is sort of a constrained resource, right? And what can happen is that these packets, while you'll receive these updates, while the source will probably receive more updates per unit time, sorry, the monitor will receive more updates per unit time, these updates will be delayed, which is to say that by the time T0 dash is received by the monitor, T1 would already have spent time waiting to get processed by the network or waiting to get delivered by the network to the monitor. So it's to say that while the source was very quick in generating updates, the only result was that the monitor got those updates. However, those updates were all delayed. So they were all aged, right? So these reset values, if you see these reset values in this curve, these reset values are large age values. And these large age values are because at this particular rate of update, you sort of congested the network. Right? So now where do we go from here? I mean, so neither very low generation rates nor very high generation rates. If you have very high generation rates, it leads to more frequent but stale updates, right? Okay, and as far as the network is concerned, that's because of larger queuing delays in the network. This curve, the sample function, is what we used, what was used long back, right, to do so-called time average age analysis. And the idea is very simple. This is a sample function, and you calculate the time average, and then talk in terms of the steady state average that you get, right? And this is fairly general in the sense it doesn't really make any assumptions about packets being dropped or not, or a particular kind of network or queuing facility or packet management or lack thereof, and so on and so forth. So, okay, anyways, this is just a summary, and the point is that ACP will eventually try to minimize, or at least keep to a low value the time average age. Okay, if you use this notion of the time average age and apply to very simple models, for example, the MM1Q, it's the simplest, it's really the simplest model, but you still can gain some good insight, and that's. You have a memoryless service facility. That's a single server, right? That's a circle here in this illustration, and you have a queue. It's an infinite queue, right? And the location updates enter the queue, and they're serviced in a first come first served manner, right? And once the service completes, the update is delivered to the monitor. So the completion of service implies the monitor gets it. If you calculate this time average age, which I'm calling age of information in this plot, I mean, you will see that there is this nice ball shape to it, and there is this throughput, which is essentially the rate at which location updates must enter, right? At which age is minimized, and in fact, the exact value is around 0.53 for this particular setting, right? And again, this curve again re-emphasizes what I sort of illustrated earlier, and that is, if you look at the left. If you look towards to the left, the age is high because of lack of updates. That's low throughput values. And if you look to the right, age is high because of congestion in the network. I mean, this is because your throughput is high. And how do you know the network is congested for this system? If you look at the delay curve, right? The delay sort of increases initially slowly, but then quite rapidly as throughput increases. And this delay is essentially the system time or the total time that a packet spends in this MM1 queue. Right, and as throughput increases, this delay increases because every packet has to wait for others to finish service. Right. Okay, so this is good. This is just to say I mean, this is just to make sure that we are on the same page with our age versus delay. It's a typical thing that people confuse, right? But this is good. This is what we will worry about, the age part. Right? You could do it for this. Is again, these are very old results, by the way, nothing to do with ACP, right? And again, this is just to show you have lossless systems here, no packet management, and so on and so forth. And there are these three curves for these three simple enough systems, right? Again, age versus server utilization. Age is, that's to say the time average age, and you get these nice curves, right? So you have this AOI minimizing update rate excess. Okay. Okay, so getting started with age, right? I mean, if you're interested in exploring further, right? These are two great survey papers to start. Okay. Okay, so before I just saw a comment, and maybe I'll just take that before I enter the rest of the presentation. Yeah, I mean, see, that's correct. So there is a lot of work if you look at these servers that assumes packet management. You can always discard stale messages, but remember that a certain edge server or something sitting somewhere, some queue processing all kinds of tasks and all kinds of status update packets. I mean, the question is, how are you really going to do it in practice? But of course, you're right. You could do simpler things, as are already done in the network. You could assign some kind of priorities. The age control protocol that I will talk about assumes that age packets will be treated in a best effort manner. Of course, there are even currently the network, I think, caters to 4 different categories of traffic, which are essentially about prioritization. But you're right. If you could do everything, you're right that you could simply discard stale messages, and that's exactly what packet management. Lots of people have proposed packet management have looked at this. Yeah.
I was just going to relate the question. I guess you already read an answer.
That's fine. That's okay. Yeah. No. If I can spot it, I will answer it. It's just a question of me spotting it here. Okay. So age control problem over the internet. As I already said, thanks to the question. I mean, we are assuming that these update packets will be treated in a best effort manner, which is to say the way say TCP segments are treated by the network, right? And so there's no prioritization. Any queue, you basically end up at the beginning. You just enter and there's no prioritization. You get treated like any other packet. I mean, this is another plot, and this is just to motivate that. I mean, the network conditions do matter. So it's not that it do matter. They do matter, and even using these caricatures, the first 3 in the legend are single server, single queue, again MM1. Okay, and the second is 2 queues in tandem. This is based on fairly simple analysis, right? And you can see, I mean, the age optimal rate is quite different, really. And this is not surprising. This is just to say that there is some value in, or there is some challenge in figuring out this rate. When you're trying to send such updates over a network that is not really fully known, right? I mean, in a sense, you don't really have a model. Okay. So the goal again, keep average age small, right? End to end, source to monitor. So in manner really, right? And challenges, again, not surprising. You're dealing with a stochastic network for sure. It's also non-stationary. You don't have any control over the loading that other traffic that is sharing the internet. Okay, you don't really have any control over that loading. Network conditions, of course, you don't have any control over, right? And importantly, you have imperfect network information. I mean, are these challenges novel to age control? Not really. I mean, TCP has handled these challenges forever now, right? But the thing is, age control tries to handle them for given this utility of age of information, right? And we will see how, hopefully, yeah. Okay. The method is very simple, and I'll show you the stack, the network stack architecture. It will be clearer. You'll see where ACP is. It's probably related to the TCP picture, right? But the method is very simple. Age control protocol figures out a good rate at any time, at the beginning of a certain epoch, a decision instant, let's see, and basically suggests that rate to the application. That's one way of thinking about it. The other ways we can, architecturally speaking, the other ways you can enable the same thing, right? So you want ACP to adapt the desired status update rate, okay, over this end-to-end path. Adapt in response to the network conditions. There's very limited related work on systems, right? And it's sort of an opportunity too for people who care to do systems, right? And of course, if you already shared 2 survey papers, one of which is very recent, and the second survey paper actually is a great start. It covers a lot of things that have been worked on with this age of information. Okay, I will start with this trivial abstract, this fairly very simple abstraction to motivate a good age control strategy. Later in the talk, I'll tell you why this got us in trouble, but that's for later. Right. So here's the deal. If I'm looking, let's say that the source is feeding into this 3-queue network, right? And so the source updates are entering the queue on the left and exiting, going to the monitor, at the end of the 3rd queue. The 3rd queue spits out updates that go to the monitor. Now, if this is the snippet, this is a random snippet I see, it's probably not good. Okay, right? Which is to say that you have these packets, these update packets waiting for each other. I'm assuming all packets are of the same source here, just to make it simple, right? Okay, right. So there's no other loading rate, right? So you have your update rate is probably higher than it should be, simply because your packets that are, you have these source updates that are backlogged behind updates of their kind, right? So you would expect age to be higher than the minimum possible, really. Now here you have these empty queues. Not a good idea, right? I mean, you have queues where you don't have any updates of your source. That doesn't seem like a good thing too. It seems that as far as this pipeline is concerned, pipeline of queues is concerned, you have a really low update rate. You want to push a little harder, meaning the source wants to, or ACP wants to set a larger rate. This is the ideal snapshot. Of course, it's the ideal snapshot. I've made a lot of assumptions here. It's deterministic service, really, right? Okay, I'm assuming that all these servers are identical and the service is deterministic, so this beautiful picture emerges, right? But the point is that you want to, given the end-to-end path over the internet, it's naturally your packet will go through multiple hops, right, or multiple router queues, right? And you want to make sure that you have enough updates, but not too many of them in this network, right? Okay. Okay, now that was a deterministic picture. If you move away, and it's kind of difficult to do it for very complex systems, but let's if we did it, it's not difficult for a two MM1 queues in tandem system, right? And you can see the first server, the service rate is set to 1. X-axis, we are changing the service rate of server 2, right? The server 2 is a packet enters the queue of server 1, and once it finishes processing, it enters the queue of server 2, and then eventually it exits server 2 and it's delivered to the monitor, right? So as you can see, and there are various things you can see here. If I look at the point on the left, where in the server 2's rate mu2 is also 1, right? You can see that the total backlog is slightly more than 1.5. I mean, it's less than 2, slightly more than 1.5, right? And the backlog is the same in each queue, right? As you increase server 2's rate, as you would expect, which is to say, because server 2 is now getting faster, right? You would expect that the backlog is mostly in server 1's queue and becomes smaller and smaller in server 2's queue. The point is this: even in this case, while it's a simple abstraction, it's no longer deterministic, right? Even here, you probably want to do a decent job of filling all queues, unless one queue is way much faster than the others, than the other in this case, right? Okay, age control protocol. We'll now get into the protocol itself, right? There are these publications. I guess these slides will be posted, so you can take a look. As we go down, at times you might see ACP plus. It's just the most current version of the code, okay, and it's better than the older one. Anyways, it's just so that you don't confuse yourselves, or I don't confuse you as a result. So here's the stack, the networking stack that we are proposing, right? I mean, if you're familiar with the TCP/IP stack, this shouldn't be a surprise. As supposed to be a transport layer protocol, it's doing end-to-end control, right? And ACP sits over UDP. UDP doesn't care for it doesn't care for it doesn't guarantee any delivery, and we don't want delivery to be guaranteed. So UDP is very nice, right? And ACP sits over UDP, which is to say it opens a UDP socket, right? And of course, the control algorithm is an ACP. The source interfaces with the ACP. So the source doesn't really know what kind of a network it is talking over to the monitor, right? Okay, yeah. And of course, source ACP, the goal is that it suggests some rate lambda, and it does this ever so often to the source, right? And of course, if you have multiple sources, they'll open multiple ACP sessions, right? The standard TCP thing. Okay, nothing radically different, right? Okay, this is a basic timeline. The first part is fairly straightforward. You need to get some initial estimate of the network, right? And of course, you need to open a UDP socket. So that's open ACP. You need to get an initial estimate of the network. The easiest thing you can do is calculate the RTT. You send it back, you send an update and see what the RTT is. Okay, and you maybe send this update about, do this around 10 times to come up with a reasonable estimate of the RTT, right? Okay, and once you have that, you're like, okay, I now know something. And now I can initialize my age, initialize my rate. What do? I say my initial rate is 1 by RTT, whatever, right? That's just the starting rate. Okay. There's another thing here, and that's important, and hopefully this won't confuse, is, as I said, the update business has to do with getting an initial estimate of the RTT. This has nothing to, the age control has just started now. Once I get the ACK, that marks the beginning of my first epoch, first control epoch. That's the first time I make a control decision or try to make a control decision, right? Okay. The control decision is about setting rate. As I said, this first epoch, rate is set in a simple manner. You just say it's 1 by RTT, right? Okay. Right, because you don't really have much else, you don't have much information really, right? Okay. Once you have done that for a certain period of time, right, and we do this for till a total of 10 updates have been sent for now. Okay, right. For a certain period of time, the source will send updates at that set rate. Okay, right. And for every update, the monitor will revert with an ACK. The ACK here is not for reliability. We don't really care whether the packet got delivered or not. Right, but in case it did get delivered to the monitor sends back an ACK, and this ACK, these ACKs that we get are important for estimating the network. And in fact, these ACKs also help us get around the problem that the source and the monitor are not time synchronized. Okay, and remember, the source wants to know the age at the monitor. Only then can it do the control. The source the source ACP needs to adapt the rate of the source. Okay, so that the age at the monitor is sort of minimized. So clearly the source needs to have some reasonable estimate of the age at the monitor, right? And that's where these ACKs are useful. We will look at a few of these things in detail. Okay, right. So epoch K, that's decision instant K, right? And at every epoch, the source ACP does the following measurements. It first measures the average age at epoch K. Of course, it's its own estimate. The curve will look similar to what I have shown above. The only thing is that D1, which if we were looking at the older picture, would have been the time A1 was delivered at the monitor. D1 is now, in fact, the time the ACK corresponding to A1 was delivered at the source ACP, right? Okay, right. Therefore, the reset value is also the round trip time, which is to say the time that elapsed between generation of A1 and reception of ACK at the source ACP, right? The other thing that you want to maintain is that you want to calculate at epoch K is the average backlog. This is again, right? It increases by 1 when you send something. When the source sends out something, it decreases by 1 when an ACK is received. Okay, and we ignore acknowledgements that are of older updates, right? Okay, right, and you calculate a time average backlog. The time average is over between the current instant and the previous epoch. Okay. Once you have delta K and BK at epoch K, ACP also calculates the change in backlog. Okay, and the change in age that happened, over these two consecutive epochs. That is in this case epoch K and epoch K minus 1. Remember that K minus 1, ACP must have set a certain rate, right? And as a result, at time K, you would expect a certain change in backlog and a certain change in age. And at time K or epoch K, you're essentially measuring those, measuring BK and delta K. Right. The other thing that ACP does, and this is just to keep a track of what the network is up to, is whenever an ACK is received, it updates the RTT. It's just an exponentially weighted moving average, similar to TCP, right? And we also keep keep an average of the inter-ACK delivery times. This gives us a sense of what the real throughput of the network is. Okay, I mean, which may be different from the rate at which you're trying to push because of various reasons, like errors, for example. Anyway, you have BK and delta K. I will just impute. I mean, clearly there are 4 possibilities at epoch K, right? One possibility is that the backlog increased, the backlog in the network increased over the last since the last epoch interval, right? And the age also increased, right? That's the leftmost. And then of course you could have the backlog reduced, but the age increase, and so on and so forth, right? And for each case, I mean, it has to be one of these 4 cases. These are mutually exclusive cases, right? And for each case, ACP must now decide, okay, based the first decision that ACP makes is whether it should increase the backlog over the next interval, or should it reduce the backlog, and by how much. Okay, once it's figured that out, it maps this desired change in backlog to the rate of updates. Okay, the rate of updates, that is, as I will say, lambda k, the rate at which the rate that gets set starting at epoch k, and will be set up to epoch k plus 1. Okay, but in any case, I'll just do a few cases here. Okay, let's consider the first case. This is just an illustration. The ball is just to mark high congestion and low congestion, really. I have a situation as ACP source has measured a backlog change greater than 0, okay, and an age change also greater than 0, meaning age increase and backlog increase, which is to say that the network got more congested, and this congestion led to an increase in age. So this when ACP sees this, ACP is like, I must now reduce the backlog. Okay, so it does that, and let's not worry about it. You can look at the details. It also does it multiplicatively in case this condition happens multiple times, right? Now let's look at this other case. This probably is a little different. Yeah, it is. Right. So now it can also happen that your backlog reduced, which is to say that the congestion reduced. However, age increased. If that's happening, then you're actually loading the network, lightly, and you probably want to push it a little more, which is to say you want to increase the backlog, right? And you could do that. And whenever we increase backlog, we go slow, like TCP does. So it's additive increase. When we reduce, we also do multiplication. Okay, I will skip this, folks. I think I'm running out of time here. I would like to also show how it works, right? Okay. Okay. So for each one of those four possibilities, the action is about a certain choice of change in backlog. The action maps to how much must I change my backlog in the network, right? And that can be mapped to a certain source rate. This is very simple, the equation you see here, but I will not get into the detail of this. My estimate of the inter-act delivery time, that is Z, and also RTT. This desired change in backlog, the thing I've circled, comes straight from what action you chose given those 4 different cases. Okay. Okay. Any questions so far? I mean, I will now try to convince you that ACP actually does okay. Yeah. Okay.
So I had one question regarding the cost associated with the age. So is it considered the linear function as with age, or is it something like a exponential increase cost over age? And if it is not linear, then is there a way to optimize this, that okay, like as a trade-off between the fresh updates that are going to come and the pending updates? Can it be kind of formalized as a optimization function?
Yes, yes. So, I mean, in this work, we are assuming the cost function to be linear, as I've shown you, right? I mean, it's very simple. It's just simplest version of age, really. But there are a lot of works that have looked at non-linear functions of age or other age functions and have tried to optimize them, right? And so, yes, there's a lot of work that has been done on that. So it can be done. But in the context of what I'm presenting, no, this just assumes a simple linear function.
Thanks.
But the surveys by the survey has a lot of those kind of works. Okay, so this is I mean, we want to get a sense of how this thing works. I mean, this is a control algorithm, right? And so we went to the real world, right? And of course, after doing a lot of simulations, but I'm just showing you the real world thing. It's kind of interesting, right? And you have I think this was an access point or maybe behind the gateway in IIIT essentially, and a certain data center. We used AWS, right? And so I think it was AWS someplace in Europe, right? And I think the number of hops as measured by trace route, right, was approximately 30 for what I'm going to show you, right? Right. Now this is good. I mean, see, this is we have ACP. That's the blue CDF. There are a bunch of CDFs because there are different runs we did, right? And I just put them together, right? And we have also lazy. Lazy is simple. I mean, it's not that it is not adapting to the network, but it's sort of a trivial adaptation. Why is it trivial? It's adapting in the sense that it's saying I will send 1 packet per RTT. So it is adapting to changes in RTT. So it's measuring RTT for sure, right? But it's saying that I'll send at a rate which is equivalent to 1 packet per RTT. Okay. It's good that ACPs, I mean, you would expect ACP to do better given the illustrations I showed you of multi-queue networks and so on, right? Simple enough illustrations, right? But I mean, when we saw this, right? I mean, this you would hope. I mean, otherwise, by the way, you might see that the average age doesn't seem to be much different in the sense that you have 250 milli. I think you have maybe a median of or whatever, let's say 200 milliseconds versus around 300. But remember that the RTT, that's 100 millisecond improvement. Remember that the RTT is of the order of 200 milliseconds. So given the RTT, it's quite a significant change, right? Okay. So what at least got a made me smile at that time was that, but for the fairly significant improvement in age achieved by age control protocol, if you looked at the CDFs of the RTTs, counter time measurements that we had made while we were doing age control, either using ACP or lazy, right? They were very similar. So the point was that ACP was certainly pushing more. And it seemed, at least empirically speaking, right, that it wasn't the pushing more of ACP was not causing updates to get unnecessarily delayed, right? Because the RTTs are of the order of what lazy sees, wherein lazy is only sending 1 packet per RTT. That was good. It was like, okay, it seems to work. Of course, this is for a particular setting, right? And this has no Wi-Fi in it, no access in it, and so on, right? Okay. Why does it do better? I mean, again, we saw that ACP was actually keeping backlogs quite high. I mean, the median backlog for these experiments that I showed you were around 30, right? Which, I mean, we are saying here that's equal to the number of hops, approximately equal. I mean, it's in the same ballpark, right? And remember that there's a CDF of the average backlog. Right? Lazy, of course, has an average backlog of 1, right? Okay, right. So I think I already said this. Okay. So here's the deal. This is an interesting story. So we got really excited about this. I mean, if you're a systems person, you probably will, right? And we sent this to WowMom, and we got some good reviews, some critical reviews, but good reviews, and it got accepted. Good, okay. And we went there. I mean, okay, I didn't. My student did, and she gave a talk and stuff. She again got good feedback, but it turned out that this picture, was not necessarily a good one to show them. A lot of community there are people who do congestion control. Okay, they do TCP congestion control. At least during that WowMom, that was the case. I don't typically send to WowMom, but that WowMom was the case. And it took us some time to realize that this caricature that we used to explain a good age control strategy is in fact a good everything strategy. I mean, it's kind of obvious, right? Right. If you look at the ideal snapshot, given this whole deterministic setting, this is exactly what is throughput maximizing. You can't do better when it comes to throughput, right? It's certainly delay minimizing, right? And I've already told you, and I hope you agree, it's also age minimizing, right? So what this led to was the good thing, of course, was right that we suddenly were told that we were told by this community, and I'm not saying all of them, by the way, the couple of people we ended up talking to, right? That what, the TCP is already doing this, right? We have these TCP is no longer that good old loss-based congestion control, right? And TCP has gone way past that, and we are getting really high throughputs at low delays. We are already doing this, right? And so naturally we are like, okay, we got to look at what TCP is up to, right? And that's when we said, okay, you can't ignore TCP, right? And for good reason. I mean, this thing just it stays. It is just there, right? And it has, as I will show you, it is not just one. There's no notion of one TCP. I mean, there's history of congestion control, and I'm sure my student here has probably only shown the big ones, right? I mean, I'm sure there are many more papers and many more proposals than the ones I'm showing you here, right? And for those who may care, 2005 cubic is what comes by default with I'll say Linux or Ubuntu, Ubuntu for sure. Right, and 2016 BBR is Google, okay, and Google BBR, and of course, and we'll see. These are different colors, and they have different philosophies about how to estimate the network. The good old ones are the loss-based, right, and then I'll very quickly tell you how they are different. It's very interesting, but it's amazing that TCP does what it does so well, or seemingly so. Okay, so. This is the summary we got from WowMom, right? And it was like the TCP congestion control has evolved from keep the pipe full high throughput and delays to high throughput and low delays. I mean, this is the panacea of everything, right? I mean, high throughput and low delays, we're done. And this is, by the way, end to end. This is not just the wireless access. This is not a millisecond delay on access that 5G is promising or something. This is end to end, right? So low delays and high throughput, good. Of course, we set down this track that, okay, what does this mean for timeliness? I mean, can we answer the question? Typically within the age community, TCP was thrown out saying that, oh, you know what, TCP case for reliability, there's going to be a packet error and then TCP is going to go crazy and the age of the resulting updates at the monitor are going to be really large. And you can show that. I mean, you can do a simple simulation with TCP, make have packet drops because of some crazy wireless access, and you will see that TCP age because of TCP goes crazy, right? So in everything I'll show you next, we have made sure that TCP is not suffering because of end-to-end drops, okay, right? We have sort of ensured that the kind of experiments we do, TCP congestion control is not bogged down by drops because of things that have not to do with congestion control, okay? Like loss-based congestion control will keep pushing and because of too much queuing at a router, and that I can't stop, right? But there's no wireless access drops. The end-to-end paths we've chosen are all AWS. We have not seen any drop. We have not seen any enter. It's amazing. There's no retransmission by TCP. There's some duplicate acts, but no retransmission by TCP. Okay. So just to make sure we're all on the same page, how TCP views the network. This is again a caricature, but an often used one. TCP, as far as it is concerned, it's a pipe, okay, and this pipe has certain base RTT. This is the RTT you would get in case TCP just sent one packet. In the case of TCP, it's a segment, and waited for an act for that. That's your RTT base, okay. So there's no congestion because of too many packets being sent, right? And of course, this is bottleneck bandwidth, and that's like the bandwidth of the bottleneck link, okay, given that you have a path which has multiple links, right? Okay, wonderful. If you think in terms of RTT base, and if you think in terms of how RTT increases as my load increases, load is throughput, okay, or in the case of ACP, it's the source rate. In the case of TCP, it is the average, it's the average throughput you get, or the rate at which segments are being shipped out, right? Right. If you look at the red line is the deterministic picture. This picture is, by the way, motivated by the BBR paper. They don't talk about steady state, but it's sort of motivated by them. I mean, in steady state, in the long run, given a deterministic system and finite buffer queues, which is what is the case in the network, right? I mean, you will see RTT base till you hit the bottleneck bandwidth, till the throughput hits the bottleneck bandwidth. After that, in steady state, things will explode. They will not explode. Okay, I mean, you will see an increase in delay because packets will now wait for other packets to finish, and then you will enter the buffer limited region, which is where you will see packet drops. I mean, this is a finite queue, so you will have packet drops. If you think of a stochastic system, things are a little more funky. I mean, you don't have this very rapid, this sharp increase. You have this. You can do a simple simulation, in fact, for a simple memoryless system with which is buffer limited. Right. This is steady state, but the other good realization when we did this was that these protocols don't care for steady state. There's no notion of a steady state, right? And what they care for is this changes in the transient. They're interested in the time evolution. So if I look at the time evolution, and this is from BBR, in fact, in the paper, right? So up to a certain, again, they assume a deterministic. The assumption is, even if they don't say it, the assumption is deterministic. The system is deterministic. The service rates are deterministic, and so on. Right. So you will see you keep sending packets as you increase the load from 0 to bottleneck bandwidth, your RTT will stay fixed. It's not going to change, okay, because these packets are still at a low enough rate wherein they won't get queued or they won't suffer any queuing delays. But beyond that, as the rate increases, right, you will see a linear increase in delay, right? And then finally, because eventually, as you will get fuller and eventually full, so much so that packets will get dropped, you will see saturation, right? You will see that the RTT will get saturated. Now, this picture is very key because it sort of puts into perspective what TCP has achieved over the many decades as far as congestion control is concerned. Loss-based congestion control has traditionally worked in the buffer limited region. The way, and I'm not an expert in TCP, right? But I mean, my understanding based on what my students told me and a little reading I have done, I mean, the way they know that the network is getting too congested is when there's a drop, okay, which means you're pushing the network into this buffer limited region, right? You're pushing hard enough that it goes into the buffer limited region, right? Packet loss indicates congestion, and that's when they work on it. Okay, that's when the congestion control sets in. Delay based says that, hey, you know what? I'm not going to push that far. I'll stay in this linear region somewhere, and I think Vegas is a good example, right? Hybrid. This is from BBR, by the way. I mean, they say that our goal is to achieve bottleneck bandwidth at RTT base. right? Which is to say that knee, that initial knee that here. This is like a panacea, right? In the sense, if I can do that for a deterministic network, I'm doing optimal everything. Okay. And this is sort of the, I don't know whether it's the holy grail or they're claiming that they are actually achieving it. They are not achieving it. But in any case, that's where they want. That's the operating point that they're tracking, that they want to track. Of course, things are very complex. It's not a deterministic network. And there's this paper, it's not cited here, I think, but there's this paper by Kleinrock, I think it's 2017 or something, or 2018, where he sort of makes a case that BBR may in fact be tracking, maybe trying to optimize forward the other network utility. But in any case, that's a separate story. The point is this: when we saw this, right? So this is exactly the high throughput and low delay point, because you really can't get a throughput larger than bottleneck bandwidth, whatever you do. You really can't, right? I mean, you can increase the load for all you want, that's fine, but the service rate is restricted by bottleneck bandwidth. And this is the lowest delay you can get. So this high throughput, low delay, wonderful, right? Okay, I will skip how we quantified aging by TCP congestion control algorithm. And the challenges are that TCP uses segments. Even before a segment is created, data lies in the send buffer and age is there. So you can read this paper and it is a recent workshop paper, and we detail how we do this. Now, let me not just waste time on that, right? Okay. In summary, we ignore aging of bytes in the TCP send buffer. This is before segments are created by TCP. And then we treat each TCP segment as an update. Okay, so remember, segment sizes can be different and all that, but this is just to get some sense of how aging using a TCP congestion control algorithm happens, right? And we assume it's the segment is fresh. As soon as the segment is created, it's fresh information, right? And of course, as I've already said, we pick networks wherein the segment losses are negligible. Okay, again, now let's do the simple thing, right? We looked at various configurations, right? And this is like a laundry list of congestion control. One of the things you want to see here is for BBR, we also chose different receiver memory configurations. And it's kind of interesting. We did this for a reason, and you'll see, right? Okay, receiver memory, if the receiver memory is too constrained, then congestion control can't push larger than a certain rate. Okay, the throughput is sort of constrained by the receiver buffer. The receiver buffer gets full, the receiver will ask the sender to stop. That's flow control. Right. So here's the deal. This is age versus throughput. This is age for TCP as aging, TCP, and also we have ACP here, right? I mean, ACP is here, by the way, right? So it's very low throughput, right? Okay, but let's look at TCP first. We have BBR D1M3. It's 200 megabits per second. 200 megabits per second is a huge throughput, right? And of course the age is larger. Okay, certainly it's sort of shifted with respect to ACP. Again, I'm showing you the many trials I did. I mean, we did. Right? Now, what is interesting and initially was a little disappointing. I mean, of course, right? And this thing is actually high throughput, not as high as BBR D1M3. It's D1M1. It's a small receive buffer, right? But it's kind of high. It is 100 times what ACP is getting, right? But the age is kind of low, right? So we have for BBR D1M3, I can say this, and I can say this for others also, by the way, but for D1M1. Okay, I mean, I have not spent time on the others, right? But here you go. What do you do about this? I mean, this was kind of a shock to us, right? I mean, it was as if the knee was actually being achieved in some manner. But so we, of course, you zoom into it. Not a big deal here, right? One of the things is that this 100 Mbps throughput, right? And it's 100 times what ACP is optimizing age at, right? Or is sort of on an average picking, right? And a part of it is 10. A factor of 10 is explained by the fact that TCP segment sizes are much larger than ACP update sizes, and we have no control over TCP segment sizes. We are not really, we are not changing them, right? But there's this other factor of 10 that is explained by the fact that BBR is actually pushing segments at a faster rate. So it's kind of really weird. We have forget the larger segment size because the rate at which a packet will get serviced, given it's in the server, is very quick. I mean, these are AWS links, right? So most of this delay, most of it, I'm not saying waiting time, right, in the network. At least that's in our experiments, right? So you have the situation where in the interact times of 1.16 milliseconds and interact times of 10.4 milliseconds are giving a very similar average age, right? That's one takeaway from this, right? This is for now ignoring the disappointment that BBR D1M1 was actually doing very well age-wise, right? So this was kind of surprising to us. We had not really imagined this. I mean, such a range. I mean, this is at least one order of magnitude if I forget segment size, okay, or throughput, that is, and the age is pretty much the same, right? And this is repeatable, by the way. right? So relatively flat age for a large range of update rates. Okay. Okay. So now of course, you have to write a paper, you have to say something, and we said, oh, you know what, great, but ACP is doing it at a much lower throughput. Of course, the good news was, it's not the most exciting result, but we realized later that basically congestion control was barely kicking in for BBRD1M1. It was too constrained a receiver buffer for the kind of path AWS to AWS provides, right? And so that was okay. So we are happy. You know what? It was like basically, if there's no congestion control happening really to push, and then we can't do much. It's just a fluke that receive buffer ended up being small enough, right? So that's good, right? What about shared Wi-Fi access? Very quickly, I think I have 4 minutes, right? And let me see what I can do here. This is important in an IoT setting. Remember also that when we is minimizing age or at least trying to keep age small, and in that process is the throughput, the end-to-end throughput is very small, right? It is less than 1 Mbps. We are like, this is good news, right? I mean, it should really work well for access unless ACP does something funny over the Wi-Fi access. Very well, as in you would expect that even with low rate Wi-Fi access, you could have many nodes, many ACP sessions, sharing that access, because the throughput at which age seems to be getting minimized is quite small, right, for any given ACP flow, right? So, okay, shared Wi-Fi access. Very quickly, right? I mean, we did up to 80 sources. I'm showing you a snapshot. X-axis is number of sources. These are sharing the Wi-Fi access, all connected to the same Wi-Fi access. We use the Orbit grid. It's in WinLab. It's a very large physical grid full of physical wireless devices, right? They're all very close to each other. So it's a high density setting, right? Look at the blue curve here, the bottom blue, right? As we go from 1 to 2 to 5 clients or 5 sources, ACP's age stays pretty same. It's as if ACP clients, they all have independent ACP flows to some AWS server, right? Okay, and these clients, at least up to the number 5, are not affected by other flows, right? On the other hand, sharing creates problems for TCP, and not surprising. The bunch I have circled put in an oval are all TCP, right? Of course, when you have only a single, which is the very beginning, you can see that TCP, especially BBR, D1M1, and so on, BBR doesn't do that bad. I mean, there's a difference. ACP does slightly better. That's fine. But things get really bad as sharing happens. Okay. So clearly, at least for, I mean, certainly the TCP community can't say that. When you're sharing access, they're still doing very low delays and so on at high throughputs. Look at the throughput picture. As you would expect, and this is simple. I mean, I'm amazed at this, and it's not really surprising. But if you look at the top bunch here, right, it's TCP. By the way, we have a 12 Mbps Wi-Fi. I mean, I think I forgot saying that, right? TCP saturates the link. It's beautiful. I mean, we go from 1 to 5 sources, and in fact, you went to 80, and you'll see it saturates the link. It's beautiful. I mean, these sources share together and ensure that the sum throughput is close to what you could expect given a 12 Mbps Wi-Fi access. Right? ACP, I mean, okay, because these nodes, these paths, these 5 different paths starting, are acting as if the other doesn't exist. They don't seem to be impacted by the other. You don't really see much of an improvement. You don't see much increase in throughput. This is more or less the per node throughputs per source throughputs are the same as far as ACP is concerned, right? Okay. So TCP flows saturate the Wi-Fi access. I've already said, they fully utilize the bottleneck. The bottleneck clearly in this case is the Wi-Fi link access, the Wi-Fi access. It's not the AWS that follows, right? ACP flows seem oblivious to each other. Update rate continues to be limited by the path beyond the access, which is to say the Wi-Fi access is not age constraining. It's the seemingly very fast pipe beyond it. And of course, one seeming reason for that, and we still have to think of, we're still working out the details, is maybe that that AWS part is quite loaded by other traffic, and that's what, and the delays that are suffered as a result of that other traffic are what matter to age control more than this notion of a bottleneck link rate, which is key to TCP, by the way, right? You can go all the way to 18 nodes. These are actual experiments. Okay, so I mean, and we're happy to share the details in case somebody is interested. If you look at the ACP curve, which is the solid line, right? If you look at the initial part of the curve, this is solid line for 6 Mbps Wi-Fi access, right? You can see there is this region in the solid line, the initial region, the oval. If you look at the access bottleneck link bandwidth isn't constraining the path beyond this, which is to say that these paths are behaving as if they're alone. The age minimizing rates are close to what you see when only a single path is working on the same network. But beyond a certain number of nodes, you see that the access bottleneck link bandwidth is the one that constrains. And how do we know that? I mean, your sum throughput sort of starts flattening. You see, as far as ACP is concerned, the sum throughput starts saturating. You can see this for different settings. Okay, for example, 12 Mbps, again, you have these two regions. Of course, as 6 goes to 12 and 12 becomes 24, the region or the number of nodes for which you have interference free, if you will, or for which age is constrained not by the axis, but by the network beyond, the really fast pipe beyond the axis, beyond the Wi-Fi axis. I mean, the number of nodes become larger and larger in that region. Okay, right. So, I mean, that's not particularly surprising though. But this also tells you that ACP is doing a fairly good job at sharing the access. Right? These are independent ACP paths that are running on these nodes. So there's no real centralized control. You know what? I'll skip this. Let me skip this. Don't worry about it. I mean, the takeaway here was that there was a period of time when we were confused as to whether anybody can. I mean, we just wanted to make sure that ACP actually is able to operate at much fewer than 1 packet per RTT, as that is in fact optimal as access gets congested. And our results are kind of positive. And they tell us that that's indeed the case. Okay, anyways, I'll just stop. Okay, folks, thank you. And I think I've already exceeded things by. This is ACP in action. This is 80 sources, of which pi have been chosen. I'm not too sure how random the choice is, but you can see these different colors, and this is sort of the age estimates of ACP, the ACP sources, different ACP sources that are sharing the Wi-Fi access. Okay. Oh, yeah, I'm done.
Thank you, Professor Kaul, for
sure.
an insightful talk. We can take a few questions if there are any questions from the audience.
I think somebody has raised in their hand.
Thank you, Professor Kaul, for such a nice talk.
Yeah.
So my question was, so what was the, like in this work, what was the major challenge? So was it like coming up with ACP or the simulation part, or because, I mean, is there anything theoretical, like guarantee something that you are showing? So what was the major like challenging part of this work?
I mean, running the simulations and experiments is not challenging, right? I mean, it's you have to know how to do it, but it takes time. It's time consuming, right? I do think that the ACP control algorithm, right, was probably the most significant challenge. I also always say this to my students. I'm kind of surprised at how well it works, and maybe it's some really good bug in the code that makes it work so well, right? As far as the theory part is concerned, I think the good part of doing this is that, I mean, there were certain surprising things we saw in the real world, which most of the models that I have seen being analyzed never captured, right? Even the simplest thing, like for a very wide range of throughputs, age pretty much doesn't budge, for example, right? And I think we are now at a stage wherein we want to better understand what ACP is doing, and maybe also understand is it good for anything or not, right? As far as age control is concerned, right? So for now we have not done any, but a lot of this work has been motivated by the analysis that people have done, and a lot of the models that have been looked at. Yeah.
Thank you.
Yeah, sure. Yeah. Yeah, we have Chandramani. I think maybe you can go ahead.
Yeah. Hello, Sanjit. Yeah, nice talk.
Hey.
Am I audible?
Thank you. Yeah, you are. Please go ahead.
Okay. So is there any analysis of age of information for TCP over Wi-Fi, say for single hop, just within a line?
I told you, I mean, you're talking TCP over Wi-Fi, right? No,
yeah,
I mean, see the thing.
TCP or UDP or ACP over Wi-Fi, single hop, simplest setting, any analysis, modeling.
I mean, see. I mean, if you're asking me TCP as in the TCP congestion control, flow control, yes, the algorithm, basically, no, that's not the case. But if you're telling me first come first served, with all packets must be delivered and so on, yeah, there's a lot of work on that. Right. I think the reason why TCP is not analyzed is because TCP is worried about in-order delivery, and it wants to ensure delivery, which is going to lead to large age. I mean, it's not really a good age strategy. Sure. Right. And so the analysis is not, I mean, I'm not saying it shouldn't be done. I'm just saying that the age community, and in fact, I was a part of that community, which sort of initially rejected TCP. But as I can see in real networks, I think TCP does work on networks which don't really see much drops of the packet drop kind of stuff.
Okay.
Right? Yeah. So maybe there is some value in that analysis.
Yeah. Thank you.
Yeah. Oh, of course, ACP has not been analyzed, folks. And if anybody thinks it's interesting enough, please, I would be very happy to hear that, right? And as I said, we certainly are interested, right, in now, given that this has worked pretty well, I mean, there has to be something about the control algorithm. It can't be a fluke, right? And that's one. The other thing I wanted to say, I mean, these are half-baked thoughts, of course, and I mean, I think if age has to age well in this whole business of age of information, I think assuming, and not everybody agrees with this, assuming the picture of the future, right, is also one wherein of modularity, right, wherein the application doesn't really know the network, right, and different layers, right. I mean, the question that I'm interested in, and but I have not really done anything about, what I'm thinking about it is can time, this notion of timeliness, can we say that, you know what, the network will just optimize timeliness, it doesn't know about the application, and then there'll be some kind of an age socket that sits between the application and the network stack, and this age socket will do the required translation. So you could have a cyber physical system application, some function of age is its interest, but the network is like, I don't know your complicated utility. Okay, but I can tell you, I can ensure this kind of age. I mean, this is very vague term I'm putting it in, and I can tell you what it, and maybe there is this socket that can tell the application what it means for the application. For example, if you have a platooning application, okay, given that the network says these are the kind of age sample functions or age statistics I can ensure, maybe there is the age socket say, oh, you know what, the platoon speeds can be of this kind, right? And then do I really care to optimize the actual? Does the network really care to optimize the actual platooning utility, which is really complicated? Not really. I mean, but maybe if you have a good enough map between this platooning utility and, you know, what kind of age values are good or age over time is good, and if network only worries about the age while the application worries about its own utility, right? Maybe that's when age will, you know, sort of age well. I mean, it's kind of interest to me. Otherwise you are pretty much optimizing. I mean, there's another trend from this whole business of modularity, right? I mean, they want to do everything end to end. I mean, the application does everything. I'm not too sure that's scalable, right? I mean, I don't know. Okay. I think I see a hand raised. I mean, yeah.
Yeah. So one more question, like in the context of at least on the cloud and data centers as well as on the Wi-Fi side also, there's this whole attempt at deliberately introducing packet drops to make TCP react. I don't know whether you have got.
Oh, I've heard of that. TCP. Yeah. So I think it's called. It is. I'm sure my student knows what it is called. I mean, it is sort of basically before congestion happens, you sort of try to signal before the actual thing sets up. Sets in. You sort of try to signal to the source that it should probably back off a little, meaning,
right. So there are these cake control algorithms for handling buffer bloats and also.
Absolutely. That's the context. You're right. Yeah, you're right. So I mean, my student and I before we worked on AC, we worked on MPTCP. So that's around the time we came across these things. I mean, I'm not too sure in the implementations we looked at, this feature existed. I really don't know. We looked at off-the-shelf implementing that are found in the Linux kernel. Right, and that's it. So yeah, we have not studied what the impact of that could have been, but yeah, in the context of aging, that is. Yeah. So I think the next simple thing. I mean, I'm not too sure, right? I mean, if the network treats age packets better than best effort, maybe things will be better as far as aging is concerned. Yeah, please go on.
Yeah, hi. So can you view this? So you had this graph of the age achieving a minimum at some particular rate. So I mean, the only reason why you can't operate at that particular rate is because you will have these additional backlogs that will accumulate. So can this be viewed as a joint optimization of your age as well as the backlogs, the ACP protocol?
I mean, the reason. Okay, I'm not sure really, right? I mean, we could view it as that, but the reason why we see when we started, okay, and we did something very simple when we started. We said, okay, I'll increase the rate, and if age increases, I'll reduce the rate. The problem with the strategy was, in case you end up in a high backlog scenario, often increasing the rate or reducing the rate would only lead to increase in backlog, which is to say the queues don't empty soon enough, right? So you're like, okay, we need to track backlog. Because otherwise, if you are in that transient wherein you're stuck in a high backlog state, simply reducing lambda might not really help. It's not going to help. I mean, because it takes time for queues to empty, right? So then we started tracking backlog and said we want to come up with how much we want to reduce or increase the backlog. and then accordingly set lambda, and then keep doing that till we sort of empty, the queue. Yeah, so we are not explicitly trying to do this joint optimization, right? But we certainly are also using backlog and not just lambda. And I think only lambda may work in case you do not have a buffer limited system, right? But I think because you have a buffer limited system, once you enter that buffer limited zone, and because ACP doesn't care for errors, I mean, you will keep changing lambda forever and nothing will happen, right? I mean, or you have to know how much to change lambda by, which means you need to know where you are and on this nice ball and the flat region beyond that, the saturated region, right? But keeping a track of backlogs helped us get around the problem very quickly. I mean, it was something that really worked. Yeah.
Okay, thanks.
So the control algorithm, I think it's the details of it are available in the latest publication, which is this workshop paper. I mean, I'm sure many in the audience are more capable of maybe analyzing it. If there is any interest, please let me know. And of course, you can independently do it too. But in case there's any interest and you would like to know more or understand the algorithm better, we'll be more than happy to be a part of those discussions, right? And maybe somebody will be able to prove that ACP is just the most suboptimal thing, or maybe somebody will say, you know what, it's not so bad given best effort traffic. Yeah. Okay. Any other questions? And of course, the code is also there, right? And I think there's one of the slides wherein Tanya had pasted her Git repository link. It's the beginning slide of H control protocol or whatever, which has all the papers too. So feel free to play with it. We were lucky that a certain independent group played with it, and they got reasonably similar results on their setup, of course. But qualitatively, the results were similar. So that tells me that the code may not be that, it probably works okay, right? So in case you want to play with the code, that is. Yeah. Okay, any more questions? Of course, you can always send me an email, folks. I'm always happy to talk about this kind of work. Yeah.
So if there are no further questions, we can close the session. Let's thank Professor Kaul again for a wonderful talk. Okay. And I hope to see you next time for the next Tuesday's talk. Have a good evening.
Thank you, folks. Thank you for inviting me. This was fun.